Okay, so up to now we have discussed the T model. Okay, previously we have discussed the Ebert-Mott model. Now also in the next class we have discussed the T model, how we can devise the T model from the Ebert-Mott model, considering only the active mode of operation into the transistor. Okay, so this is your T model. This is the common base configuration. So in the common emitter configuration, this is the T model. So in the T model, whenever we have this is the upside down of the Ebert-Mott model, considering the active region of operation. Now if we just make this base and the collector here, collector to the right hand side and emitter here, okay, this is the same case. So we replace this RE with 1 plus beta RE due to the concept. This concept has been applied. Okay, this concept due to the voltage VB, and the RO resistance, output resistance, is due to the early effect. So this is the T model and beta IB is your collector current. Now we will replace this model, and this is the common base configuration T model. Okay, that we have discussed. So next we have already said that next we will discuss the common emitter amplifier, that means the voltage divided by a common emitter amplifier, and try to analyze the circuit with the help of this T model. Okay, so for that purpose, first we have to draw the voltage divider bias circuit completely with the AC source connected and with the bypass capacitor connected across the emitter resistance. So I'm not drawing the diagram, I'm just inputting the diagram to save the time. All of you have seen this diagram previously. Okay, this is nothing new. So this is the voltage divider bias. Okay, so this is the voltage divider bias. You have already seen this voltage divider bias previously. Okay, so now we will try to analyze the circuit. Now the step one, what I have said that the step one is here, perform the DC analysis, but we will not perform the DC analysis here. DC analysis is used to set the Q point of the circuit, proper Q point of the circuit, that means the ICQ and VCQ. Okay, so to set these two value, so proper placing of the Q point, we have perform the DC analysis. We have to perform the DC analysis, but when the voltage divided by it, what is the ICQ and VCQ, we have already discussed previously, so we will not study this here. Okay, now the step 2, AC model. Now in the case of the AC model, whenever we try to analyze the circuit with the help of this AC model, okay, so AC model we have said previously that to connect this voltage source V in, externally applied voltage source, connect this voltage source with the circuit, we have to short circuit this capacitor, and also in the case of the AC, this capacitor will also be, this capacitor, 1 minute, this capacitor will also be short circuited. Okay, like this, and this will be your ground. And as we perform the AC model analysis, so this VCC will also be connected to ground. So these are the different steps we have already discussed previously, and this capacitor will also be short circuited like this. So the three things going to happen here. First thing is this capacitor will be short circuited, so that this voltage source, externally applied V in voltage source, will be connected to the circuit, and this capacitor will also be short circuited, and this VCC, that means the DC voltage, will also be short circuited. Okay, and this capacitor will also be short circuited. So these are the steps. With this understanding, we are going to draw the model. So as we go on draw the model with the help of this understanding. Okay, so this is grounded, because this resistance is no use here, because capacitor is going to be short circuited here. So that's why to the emitter to the ground, and there is a V in supply here, there is a supply of V in here, and these two resistance, as this is connected to ground and this is also connected to ground. Okay, so these two are in parallel. So your R1 parallel with R2. Okay, R1 parallel with R2. Next, this is your output voltage V0, this is your output voltage V0, and this is your collector resistance. Collector resistance is also connected to ground. Okay, so this collector resistance is also connected to ground. This is your RC. So this is the AC model. So the AC model, we have said that previously also we have to short circuit the capacitor and we have to short circuit the DC voltage source connected across the circuit. So these two steps had been performed here. Okay, we have short circuited the capacitor, all the capacitor present in the circuit, and we also short circuit this VCC source. So this circuit comes out to be this circuit. Okay, this is the first step of understanding. And next, what we want to do, we want to replace this transistor. Okay, so we want to replace this transistor with the help of this T model, so that our total circuit will be in linear mode, or we can analyze the circuit with the help of a network analysis. Okay, now the next step is our transistor will be replaced by our T model, so called T model. Okay, so that is the case. So that's why we have to just, so this is your V in. Okay, so from the left hand side, 1 minute, there is a source V in. So V in is there, and there is a R1 parallel with R2. Okay, so this is R1 parallel with R2. Next, the transistor comes into picture. So this is your base terminal. So I'm just drawing with different color. So this is your base. From base there is a resistance, and this resistance is nothing but 1 plus beta into Re. Okay, this resistance. Okay, and there is a dependent current source is there. So this terminal is your collector terminal. Okay, and there is a output resistance R0 is there. This is R0 and this is your beta IB. Okay, so this is your beta IB. So I am just writing here beta IB, and one minute. Beta IB. Okay, so I'm just writing down here. So this current is your beta IB. This current is your beta IB current, and this is your emitter terminal. From the emitter terminal it will be here grounded like this, and there is a collector resistance present at the output terminal. So this collector resistance will be grounded like this. This is your collector resistance. The collector resistance will be grounded like this. Okay, so this is the complete circuit model. In the T model, we have seen the T model. So the first analysis in the AC circuit analysis, that we have to short circuit this capacitor, then short circuit the DC voltage source present in the circuit. Then after short circuited the capacitor and the DC voltage source, this R1 and R2 comes into parallel. So that's why R1 parallel with R2. Then this is your transistor, and next this is the RC resistance. RC resistance is also connected to ground because this VCC is also deactivated. So deactivated means this is connected to ground. So this is your RC. Okay, and this is the output voltage source. Next, this transistor is going to replace with T model. So this is the T model. This resistance is 1 plus beta Re. Okay, this resistance is 1 plus beta Re. So 1 minute, I'm trying to copy again. Okay, so this resistance is 1 plus beta Re. So and this is R1 parallel with R2. So 1 plus beta Re, this is the base terminal, this is the collector terminal, and there is a current source beta IB. This is nothing but your collector current, and this is emitter is connected to ground, and this is the output resistance. That we have already discussed how the T model will look like in the common emitter configuration. That is exactly the same, and this is the collector resistance RC. Okay, so next we will try to calculate the different parameter of the circuit. Okay, so to calculate the different parameter of the circuit, first we will try to analyze the output resistance and the input resistance also. Okay, so first is your output impedance. So what will be the output impedance? Output impedance will be seen from here. Output impedance will be seen from here. Okay, so to calculate the output impedance is nothing but your Z out. Z out is nothing but your output impedance. So what will be your output impedance? Output impedance is nothing but this resistance and this resistance, both are connected to ground, so both are in parallel. Okay, so your R0 is parallel with Re. Okay, now as we have said previously, that value of R0 is very much high. The value of R0 is very much high, so you can said that the output impedance of this circuit configuration is nothing but your RC. Okay, as this is very high, so you can calculate on your own and find out that this is nothing but your RC. Okay, this is R0 parallel with RC. 1 minute. R0 parallel with RC. Okay, so this is nothing but your RC. So this is all about the output impedance for this configuration. So next we will calculate the input impedance. Input impedance will be seen from here. So this is your input impedance. So what will be the input impedance? Input impedance, this R1 parallel with R2, this resistance and this resistance 1 plus beta Re, both are connected to ground in the same way that the output impedance is being connected. So these two are in parallel. So Z in input impedance, input impedance. So input impedance is nothing but Z in is nothing but R1 parallel with R2, this resistance parallel with 1 plus beta Re, parallel with 1 plus beta into Re. Okay, and 1 plus beta Re is can be approximated by beta Re, so it can be approximated at R1 parallel with R2 parallel with beta Re. Okay, so this way we can try to calculate the different parameter of the circuit. So two parameter I have already calculated, the Z out and the Z in. Okay, these two parameter. Next we will try to calculate the voltage gain of the circuit. Now whenever we try to calculate the voltage gain of the circuit, 1 minute. Okay, so next we try to calculate the voltage gain of the circuit. So before calculation of the voltage gain, first write down the V0. Voltage gain is nothing but the output voltage divided by the input voltage, that means V0 divided by Vin. Now what is V0? What seen from the circuit is current is flowing through like this. Current is flowing through like this. Previously I have also said in the common emitter configuration, that means current is flowing through like this, and also we have calculated the output voltage. Okay, we have calculated the output voltage across here. Whenever we have calculated this gain, okay, 1 minute. So this has been written here that our voltage gain is nothing but V out divided by V in. Okay, so V0 is nothing but this beta IB into Z out. This beta IB is current is flowing like this, and this resistance, this total resistance, these two are in parallel, so it will be replaced by a single resistance like this. It will be replaced, both these two resistance will be replaced by a single resistance. So that will be your, so this will be your current source like this, and I'm just drawing the output section, and the output impedance is like this. So this is a Z out, current is flowing through this, so voltage drop will be like this, but so voltage drop will be negative because in the reference voltage V0 will be calculated like this potential will be calculated like this. Okay, so V0 will be negative, so V0 will be negative of beta IB into Z out. Okay, so beta IB into Z out. So this is nothing but the V0. Now this to calculation of the voltage gain, we must know the V in. Okay, so IB, what is the value of this IB? First calculate the IB. So IB is nothing but, this is your IB. So current flowing through this is your IB. So IB is nothing but V in divided by 1 plus beta into RE previously. Okay, so that will also be approximated at, so I am just writing, you can see these two are in parallel, so voltage drop across here is also V in, voltage drop across here is also V in. So current IB is nothing but V in divided by 1 plus beta RE, voltage divided by resistance. So IB is nothing but 1 minute, V in divided by 1 plus beta RE. So V in divided by 1 plus beta into RE. Okay, now this can also be approximated at 1 plus beta RE is beta RE. Okay, now IB can be replaced by, IB can also be replaced by, that means you can see that this equation IB can also be replaced here. So IB can also be replaced as minus V0 divided by beta into Z out equal to V in divided by beta into RE. Okay, so I am just replacing this IB in this equation, so this beta and beta will be cancelled out. So your voltage gain nothing but AV is V0 divided by V in is nothing but minus Z out divided by RE. Okay, so your voltage gain AV is nothing but, Z out is nothing but, what is Z out? Z out is nothing but your RC. So minus RC divided by Re. Okay, so this is your nothing but your voltage gain into the circuit. I hope it is clear to you that what is the voltage gain and how the voltage gain is being calculated from the circuit. Okay, this will all about the voltage divider bias, this circuit analysis. So we have analyzed this circuit with the help of our T model. Okay, so next, okay, this is all about so next assignment with you, without the bypass capacitor, if we don't use this bypass capacitor, one assignment will be provided to you that if you don't use the bypass capacitor, what will be the different parameter of the circuit. That means the input impedance, output impedance, what will be the different parameter. Okay, so if you eliminate the bypass capacitor. Thank you.